We are ready.
Okay, so good evening, everyone. My name is Gabriela. I am the Brazilian representative for Interalage, the student network of Alage. And today we are honored to have Dr. Walter Gonzalez with us. And before we begin, I'd like to take a moment to introduce him and share some information about our special guest. So Dr. Walter Gonzalez holds a BS in physics from Universidade Nacional de Engenharia in Lima, Peru, and a master's degree in space physics from INPE here in Brazil, and a PhD in space physics from the University of California in Berkeley. He's one of the most distinguished space physicists in our field, with expertise in geomagnetic activity and space weather phenomena. He has dedicated over 4 decades of research at Instituto Nacional de Pesquisas Espaciais, o INPE, here in Brazil, where he served as the head of Space Science Department and the Space Weather Program. His remarkable career includes researching positions at institutions such as NASA Jet Propulsion Laboratory and NOAA, and also notable awards, including NRC NASA Award and the American Geophysical Union Space Weather Award. Additionally, he is a prolific author with over 260 research articles, 5 books in space physics, and more than 18,000 citations at Google. So, Dr. Gonzalez, thank you so much for joining us today. We are all excited to hear your talk, and please feel free to start whenever you're ready.
Okay, thank you very much for the introduction. I have the pleasure then to present this talk on extreme geomagnetic activity as an invitation from the students of Alaje. And I will try to present in a short time, 30 minutes or something like that, this important or interesting topic of study in space geophysics. I had devoted some of my professional time and career in studying this the geomagnetic storms, and most recently during last 10 years or so, I have concentrated efforts on studying extreme geomagnetic activity, as I will be describing in this talk. I will define what it means, extreme, of course, and then go to the basic relationship with geomagnetic response to solar activity forcing. Okay, so I will start presenting this overview of the solar terrestrial relations that among several issues, one of the most important aspects of this relationship is the emission of solar active manifestations of the corona, photosphere and the corona, in terms especially of the coronal mass ejections that affect the Earth's magnetosphere. And as we know, as a result of this interaction, we have the magnetosphere energized, and as a result of that, the main dissipation processes are the geomagnetic storms as a global process, and and geomagnetic substorms as associated with high latitude activity. So as we know, during the solar cycle of about 11 years or so, the sun has these active regions, increasing active region as illustrated here in this white or yellowish structures, growing from small sizes or to larger sizes, especially during of course, the maximum of the solar cycle. As in the present case, in our present solar cycle, we are right at the maximum, so we are experiencing the emission of several intense coronal mass ejections. Like a few days ago, we had one that produced an very intense magnetic storm. In May of last May, we had a very strong, extreme magnetic storm as a result of this solar maximum emission of activity of the sun. Okay, and in this today I will be concentrating on on the coronal mass ejection study. Let's see how can I have put it here, the high-speed streams that also affect the magnetosphere, producing intense storms, but not as intense as the coronal mass ejection. So I will not discuss in this lecture about high-speed streams, but I would like to concentrate on. So let me close this. Okay. So this is an illustration of a coronal mass ejection, as you know. Is the most important type of ejection from the sun that affects the magnetosphere, and is usually characterized by three structures. One is a forward shock, this black circle here, that because this emission is strongly supersonic, superalbenic, and in the interplanetary medium, it propagates with faster than Alban wave speed. So it has a shock in front, usually a Mach number measuring the shock intensity of from 6 to 8 and sometimes to 10 or more. So when it arrives to the Earth, this shock compresses the magnetosphere strongly. And after that, we have the main structure that's released from the sun with the magnetized plasma, a very strong magnetic field and well-behaved magnetic field, usually of a helical type, helical structure, and it's usually called a magnetic cloud. This magnetic cloud is magnetic field, is responsible for the intense phase of the magnetic storm in the Earth. And in between the shock and the magnetic cloud, we have a kind of turbulent plasma, but sometimes the magnetic field also becomes large because strongly amplified. So in addition to the magnetic field of the magnetic cloud, the magnetic field of the turbulent region that's called the sheet region affects also the magnetosphere, leading sometimes into intense storms, and sometimes the two structures, the two magnetic field structures from the sheet and from the magnetic cloud, come one after the other, and the response of the storm is in two phases. The first phase produced by the sheet magnetic field, and the second phase is by the magnetic cloud. So usually they call two-step magnetic storm. Okay. Let's see. Okay. So when the magnetized plasma arrives to the magnetosphere, as we know, sometimes the orientation of the interplanetary magnetic field is mostly in the south direction, as it's shown here in the yellow lines, opposite to the northward direction of the geomagnetic field that encounter at the front side of the magnetosphere is called the magnetopause. In the magnetopause, these two magnetic fields interact, and when they are opposite, the important plasma process called magnetic field reconnection occurs. Especially important because it changes the topology of the magnetic fields to a common, to a join the magnetic structure, field structure, like here, like the pink field that's coming from here is propagating. It is a combination of the interplanetary field and the geomagnetic field that become attached and by magnetic reconnection, and the solar wind plasma still flowing here and pushing this reconnected magnetic field to the tail of the magnetosphere, where from north and south. So when the two fields encounter again in the tail, with opposite directions, they reconnect again, and we have also reconnected plasma, reconnecting magnetic field going in two directions, one coming back to the Earth, and the other exiting the tail from the side. So we have a kind of a cycle of motion of magnetized plasma coming from the day side, going to the night side, and then coming back. So to this motion, it's called magnetospheric convection, the convection of magnetized plasma from the sun to the direction to the tail direction, then back to the sun direction. So we have this magnetospheric convection. As a response of the interaction between the coronal mass ejection and the magnetic field, especially the currents in the magnetosphere become intensified, as shown by some of the currents are shown here by in red arrows. So in the front side, we have the what's called the Chapman-Ferraro current, or the magnetopause current. That's responsible for the pressure balance, the pressure balance between the solar wind and coronal mass ejection pressure from one side and the magnetosphere magnetized plasma pressure from the other side. So we have the current on the magnetopause that's called the Chapman-Ferraro current, and this can be seen in the magnetograms. They affect the geomagnetic field, even at the surface of the Earth. So the magnetometers can see the presence of this current by a change in the positive direction of the geomagnetic field. The other important current in the tail is this this current that separates the magnetic fields in both opposite directions. This should be in the opposite direction. So this current, this tail current, intensifies during magnetic storms because the magnetized plasma is moving and compressing the tail from both sides, and north and south, also intensifying this current also. And then inwards, closer to the Earth, at about 4, 5, or 6 Earth radii, we have the ring current. There's the famous ring current. There's a current around the Earth, and there's the closest current in the equatorial, intensified, especially in the equatorial region of the magnetosphere. And this several million amperes type of current can be seen, can be measured by the magnetometers in the surface of the Earth, And from these measurements, they construct the DST current. The DST is our index that measures the intensity of the magnetic storm. And nowadays, with many magnetometers, we can have a more a more detailed measure of this DST index, and it's called a symmetric H index, and it's composed of several, more than 10 magnetometers contributing to that index. So there is there is a definition of that the magnetic storm is intense when this DST, when the DST index becomes 100 or less, because it's a negative value or less. And when it becomes the order of 250 or something, is super intense. And when it becomes of the 400 nanotesla, it's called extreme magnetic storm. So it is a common procedure to define the intensity of the storms in terms of the intensity of the ring current, of intense, super intense, extreme. And that gives an idea of the status of the whole magnetosphere that's becoming energized by the interaction with the coronal mass ejection arriving at the magnetosphere. And it's a rough measure of the magnetospheric activity. But we also have other currents like these two here that are going into the auroral region or out of the auroral region, connecting the processes of the high latitude auroral region to the equatorial region of the magnetosphere, and becoming part of this global close convection of plasma and tight plasma, producing electric fields and currents in the magnetosphere. So the processes in the auroral region are measured also by the intensity of the auroral electrojet current that's in the auroral region, especially in the night side. And when the auroral electrojet becomes for the order of 1,000, 2,000 nanotesla, because it's an ionospheric current, it's closer to the Earth, it's called intense, very intense. And when it becomes of 3,000 or something nanotesla, the auroral electrojet current, it's called extreme extreme substorm. So a substorm is a measure of the activity of the auroral region, basically, whereas the storm, as measured by the DST or CMH index, gives an idea of the whole magnetosphere. So the storm, we call a storm as a global phenomena in the magnetosphere. Okay, so I'm not going to talk much about reconnection, because magnetospheric reconnection, because we don't have time. But as you know, it's maybe we can say it's the most important plasma process in the magnetosphere, because it describes the interaction of the solar wind or the coronal mass ejection with the magnetosphere as a process of energy and momentum transfer. So it energizes the magnetosphere, and also in the tail, it shows the dynamics of the plasma magnetic field, returning the reconnected plasma magnetic field to the Earth. So I could say that the magnetic reconnection is maybe the most important process to be studied in the physics of the magnetosphere. And I have devoted a lot of my time on studying this process since since the time of my doctoral thesis until most recently. So I have tried to follow the progress of research progress in this area of magnetic reconnection. So maybe, you know, in the next semester, by March or so, I could offer another lecture just dedicated to magnetic reconnection, if you are interested. So when we study the interaction of the solar wind or the coronal mass ejection with the magnetosphere via reconnection, we well, in the recent years, especially 5, 10 years, up to 5 years, there has been a lot of advancing computer simulation research related to this topic, doing MHD simulations to study large-scale processes involving a large fraction of the magnetopause, and also using more kinetic plasma approach, that's called sometimes a PIC simulation, PIC simulation. Also, there are advances in studying a more detailed study of the central region of reconnection, that's called the diffusion region of reconnection, in order to understand the dynamics of the ions and then even of the electrons at a smaller scale. This is the typical scale size of the ion physics in the central diffusion region of reconnection. Up there, 500 kilometers or so is the ion gyro radius, and the electron gyro radius is smaller than 100 kilometers, and just maybe 10 kilometers or so. Also, we can try to understand in this by doing simulations. But most recently, also there has been observations, but satellite missions like this one is MMS mission from NASA, the magnetospheric missions, satellite missions that has launched 4 satellites trying to study the reconnection region at the magnetopause. These satellites can become very close between them. So when they are very close, they can study even the central diffusion region of reconnection, sometimes even arriving to describing the physics of the electron diffusion region, and most easily, especially the physics of the ion diffusion region. So this will maybe a topic of, as I said, of another discussion. Okay, so intense storm, as I mentioned, is defined when the DST or CMH indexes of the order of less than 100 nanotesla, because a negative value, so it's when it's smaller, so 100, 150, something like that. This is the example I would like to show you how one can study the the data, interplanetary data associated with the arrival of a coronal mass ejection composed by the magnetic cloud here, and then the shock in front and the sheet region in between, interacting with the magnetosphere via reconnection. So in front of the magnetosphere, as you may know, there is at about 200 Earth radii, there is a Lagrangian, is what's called Lagrangian region, Lagrangian point. It is a region where the gravitational field of the sun and the gravitational field of the Earth cancel here in this, so it is much closer to the Earth, of course. So in this L1 region, because it is null, gravitationally null, they have placed satellites around a stable satellite orbit, with a stable orbit satellites around that point, measuring the arrival of the plasma, solar wind plasma, the coronal mass ejection plasma, and as a monitor of for the study of solar terrestrial interaction. And so this is an example measured by the A satellite of how one can study the measurements of this satellite, plasma magnetic field measurements by the satellite when the coronal mass ejection arrives. So here's the time here, and then several parameters magnetic field. This is a component, important component BC. That's component that's perpendicular to the ecliptic plane. So as I mentioned before, when this field, BC field, is opposite to the geomagnetic field that is northward and this is southward, reconnections occurs very efficiently. So usually we look into the behavior of this BC component when trying to study magnetic storms. When this dotted vertical line, the first line here, shows the arrival of the shock, because the shock compresses all the plasma magnetic field. We see that the changes, abrupt changes in the magnetic field, temperature, density, velocity, everything is abrupt change, so kind of easy to recognize the presence of the shock. After the shock, we have the arrival of the magnetic cloud, and in between the sheet. The magnetic cloud is recognized as a region where the components of the interplanetary field, like this BC, when they change from one direction to the opposite, so in this case, going from south to north. It is a rotation because it's measuring a helical magnetic field. So a helical magnetic field, the first part can be south or north, and the second part, the opposite part, will be the opposite, but south, in this case, the south, north. And as we know, we expect the southward part of this BC will be the source of the storm, because the DST is changing, showing a big change, grow up to near 200 nanotesla. So it is more than intense storm as a result of the arrival of this southward structure, southward magnetic field and plasma. The southward field is about minus 20 nanotesla, which is kind of large field. During extreme storms, it can get to minus 50 or 60. So. But this is already a large kind of intense to 200 nanotesla. So the speed in this case, the solar wind arrived only 400 kilometers per second. And then there was a high-speed train coming from behind, but that didn't affect much. It changed again a little bit the behavior of the ring current intensity, but the most important structure in this case is this magnetic storm that occurred here as a response of the arrival of the southward field. Okay, we go now to super intense storms. As I mentioned, is the definition is around 250 nanotesla. Since the start of the space era in 1957 until very recently, we had all these super intense storms with the DST indices going from 250 to 400 and in this case, March of 1989, almost 600. So here we have all the super intense and extreme also events, storms that during the space era. In yellow is shown the extreme storms that we'll be discussing later, where the DST is more than, I'm saying, in absolute value, more than 400 nanotation. Recently, in this year, we had another extreme storm that's not put here of also of 400 minus 400 nanotesla in May. You remember in May of this year that we discussed in our last collage meeting. In this table, some of these events have asterisks, like this case. That means that for these events, we can find measurements of satellite measurements of interplanetary plasma magnetic field at the L1 region that I mentioned before. So we can find data for the example that we just discussed. For the super intense storm, then, of the table that was shown in the previous table, the average value. These are average values of some of the parameters of the super intense storms. The DST was an average 320 something. This is an average of all those events. The solar wind, average solar wind. So one can say that this average values is kind of representative for the occurrence of super intense storms. So the speed needs to be larger, like almost 800 kilometers per second. The magnetic field is also large, 42 nanotesla. The typical magnetic field in the solar wind is 5 to 10 nanotesla. And the software field of all these events, the software field that governs reconnection is about 35. The average value is kind of large value also. Electric field is the speed times the BC is about this value, 10 millivolts per meter, 24 or so. The density is also kind of medium to large value. The typical densities are from 5 to 10, but it's about 25. The pressure also is a large value, 25. Typical values are only up to 5 nanopascal, and this can 25 or 26. So, of course, as expected, all these parameters show large values because represent the super intense storm. Okay, going on to extreme storms, the definition around 400 nanotesla. We remember the typically discuss extreme storms, that of the Carrington storm that historically occurred in 1859 when the magnetometer in Bombay in India measured a large change in the H component of the geomagnetic field, a very large change in that H component of more than 1,000, almost 1,500 nanotesla. So at that time, of course, we didn't have a DST index, only this magnetometer H measurement, component measurement, from which, of course, the DST is constructed, but we need more stations, of course, to make an average. But at least this shows the kind of order of magnitude of that event in the delta H change associated to the DST index. This is more than 1,500 nanotesla change. Carrington at that time observed the sun. Carrington was a solar astronomer, and he one day before the magnetic that extreme storm, he observed in the sun a very big large area emitting produced probably a large coronal mass ejection, more intense than I just put it here because we didn't have the measurement of Carrington. But for illustration, I put it here the solar active region that was observed for the recent extreme storm of last May, for which the DST was 400. And for the Carrington storm, they discuss as much larger than, more intense than that, but probably the solar active region may have been larger than in area, maybe more intense. So this it's a large fraction of the solar area. For that Carrington event, historically, it was interesting to find many observations of auroras that occurred at that time at the middle and even lower latitudes. And this is Central America, and there are auroras reported even in Chile and Argentina. It is difficult to find because more than 150 years ago, so one had to trace in the newspapers or something of that time. But it was reported several auroral events during that time. Coming back to this table, so the yellow painted events are those who have more than 400 in absolute 400 nanotesla. So these are the extreme storms that occurred, plus the last one that we had in May of this year of 400 nanotesla. So only 5 or 6, only 6 events, 6 extreme storms. This is a very much discussed extreme storm of March 13 of 1989, when the DST reached about 600 nanotesla, but there was no interplanetary data measured by satellites for this storm, because it was so big, so intense, that the monitors in the satellite, the detectors of the satellite didn't work. They became saturated or malfunctioning. And unfortunately, that happened during many extreme storms, because the event is so extreme that the detectors were not calibrated for that kind of intensity. So unfortunately, it's difficult to have data. In this example of this extreme storm of almost 400 nanotesla of November 2003, and the last one of May of this year, for which we had satellite data. So for this event, we had these measurements. The velocity reached almost 1,000 kilometers per second. Total magnetic field was almost more than about 50, or more than 50 nanotesla. The southward field also reached almost 50 nanotesla, so it's very big. So the DST arrived to 400 nanotesla. So I will show later similar table for the last May event of this year. Oh, also we have another almost extreme storm, because the DST was the DST index for this Halloween storm of October 29, 2003. The peak DST or CMA, this is a CMH kind of reached almost 350, 360, almost 400. So one can say that it's almost extreme storm. So people have been studying these Halloween storms a lot, because we have very detailed measurements of plasma magnetic field, so one can learn a lot of physics during the interaction of this type of coronal mass ejection with the geomagnetic field. And more recently, in 2012, in July, we had a very extreme interplanetary event that didn't arrive to the Earth, fortunately, because it was very big, maybe as big as the Carrington storm. This is the sun, and this is the Earth here. This is the orbit of the Earth, and we have two NASA satellites. The stereo satellite. This is stereo satellite A, and this is a B. Of course, in the same orbit of the Earth, and stereo A was located right in the direction of the emission of the coronal mass ejection from the sun. The Earth was here, so the Earth fortunately didn't get the effect of this emission. So this is showing the density and the speed measurements. So this structure was released almost 1 week after the central region of the sun, where the CME was launched. It was in the direction of the Earth, but during that time it was more than 90 degrees difference, fortunately. The stereo satellite measured these parameters of the magnetic coronal mass ejection. The shock arrived, and then the magnetic field was as big as 18 nanotesla. This is the southward field is also about 60 nanotesla or something. And this, of course, it didn't arrive to the Earth, so we don't have measure for DST. This is only constructed. This is based on these parameters. One can construct what the DST type of DST index. It may, depending on the model, it may have arrived to 1,200 nanotesla if it had arrived to the Earth. So that may have been as intense as during the Carrington storm. So, and then, as I mentioned, studying substorms, so the physics of the auroral activity, studying the as measured by the auroral electrojet, auroral electrojet current intensity. When it gets values larger than 3,000 nanotesla, it is big because it's an ionospheric current. We say that it's an extreme auroral activity. So during this Halloween storm, we have a nice study of this of the occurrence of these substorms. This is the auroral electrojet measure index. One can say it arrived to more than 3,000 nanotesla as a result of this large structure, BC structure in the sheet region of the arriving coronal mass ejection. So this is amplified. One can see the shock is here. So the southward fields in the sheet region are this. This is the magnetic cloud already, but before we had a sheet region in front. And during this at this time, this time is as here. So enlarge it here, so one can see the southward fields arriving almost to 50 minus 50. In red is the BC field, so around minus 50 nanotesla. So during this time, the auroral electrojet had values of almost more than 3,000 nanoteslas. So by studying the auroral electrojet and the geomagnetic responses, the magnetometer responses associated with the currents, one can try to understand the dynamics, the physics of the auroral region. And recently, by Otani, recently has observed that there is a very important field-aligned currents coming in one direction and coming out in the other direction. And this field-aligned, sorry, I'm sorry. So these field-aligned currents show the presence of very intense processes in the auroral region associated electric fields, and many people study substorm. When they study substorm, they study this type of structure currents, westward current, eastward current during daytime, and this it is called the wedge current because this is the type of a wedge current that's kind of coming in, closing in the ionosphere, coming out. So this connecting with the magnetosphere above. So this is, I will not have time to discuss this auroral region processes because it's more related with substorms, but it's part of the response of a magnetic storm associated with processes at a high latitude. So coming about the recent May event of this year, the sun had this big solar active region from which a coronal mass ejection, extreme intense coronal mass ejection was ejected, and the satellite in front of the Earth measured these parameters. The magnetic field also as large as 50 nanotesla. This is the southward component, this one here, also with values of 60 nanotesla something. The speed was not too big, but 750 or so during the storm. But I will show later the DST, but the KP was also another planetary index that measures the storm activity. Since the arrival of the shock and the main phase of the storm here, it had almost peak values near 9. 9 is the top of the top value of KP, so the storm was very intense. This is the DST index, so near midnight, this is May 10, 11, 10 and 11. So more or less in the midnight of May 10, we had the main phase of the storm, reaching values of almost 400 nanotesla, the DST value. Then, of course, we had associated with the storm very nice auroras, with the substorms, intense substorms of 3,000 nanotesla, so the aurora electrojets. So the auroras were observed, like in this example, in San Francisco, California, and there are many other illustrations like this one as in New Zealand, also in the southern hemisphere at middle latitude. So auroras usually, as you know, only occur aurora region high latitudes, but in these extreme events they get down to middle latitudes in the middle of the United States and New Zealand. So, okay, I think with this I will close my presentation, and I would like to suggest, if possible, that the questions that you may have for my talk, I would like to receive by email so I can discuss in more detail with you, because now I will only could answer very shortly, but maybe not, not easy to understand in just short response, but I would like to interact with you, with the students, by motivated by this talk. So I would like to receive the questions by email, and then I will discuss with you, give my response, giving some maybe references and things, so you can understand more the issue. Okay, thank you very much.
So thank you very much, Dr. Gonzalez, for that enriching presentation. And I don't know, I think we just have one question on chat.
Oh,
If you
sorry. I don't know what happened. Okay, sorry. Okay. Yeah, please go ahead. I, I don't know. Can you listen? Can you listen me?
Yes, doctor.
Sorry, what? Please repeat your comment.
Hi, doctor. My name is Gabriela. The question is mine. My question is if there are periodicities in these extreme geomagnetic storms that they are not related only with the solar cycle, because I think that these extreme geomagnetic storms occurs only in the maximum of the solar cycle. But there are another processes that another processes generate this kind of extreme geomagnetic storms.
Okay. If I understood your question, during the solar cycle, when the extreme storms occur more frequently, one can expect that the solar maximum, because we have more intense coronal mass ejection, right? Is that the question?
Yes. But
Okay,
there are other processes.
okay. So sorry. Yeah, that is. I would say that's one. We expect that that may be true for most of the extreme storms, but I didn't show that. But if we plot, say, the occurrence of the extreme storms in terms of the phases of the solar cycle, we have several examples that some of them may have some of them occur during even during the descending phase of the cycle, and even closer to solar minimum. So maybe I would say I would just I'm just extrapolating, but maybe 60 or 70% of the extreme storms may be associated with coronal mass ejection occurring around the solar maximum. But there are some interesting examples that occur maybe 20 to 30% of the cases occurred also in other phases of the solar cycle.
Okay, thank you. Yes, because my idea is that they only occurs in the maximum, but there are examples that occur in minimum. Okay, thank you.
Yeah, okay. But I think you also mentioned at the end of your question if there is another reason, another cause of the extreme storms that are not much associated with the phase of the solar cycle, but maybe with the with the magnetosphere itself. But that I don't know if that's the question. But the response of the geomagnetic field to the arrival of the coronal mass ejection depends strongly, I would say, on the orientation of the magnetic field that's arriving. So even if the coronal mass ejection was very big, associated to the peak of the solar cycle, if the magnetic field of the coronal mass ejection that arrived to the magnetosphere was not opposite to the direction of the geomagnetic field, we don't have the occurrence of extreme storms. For instance, in August of 1972, there was a very big coronal mass ejection, maybe as big as the one that I showed or that happened in July of 2012, with a speed of more than 2,000 kilometers per second. So magnetic fields probably very big. But the magnetic field was mostly in the northward direction, so parallel to the geomagnetic field. So there was not much reconnection between the two fields, and the DST only arrived to 250 or something like that. So, I would say that the most important feature responsible for the occurrence of very intense and extreme storm is of course the intensity, but the orientation, the direction of the magnetic field that's coming with the coronal mass ejection, and that is an important issue for alert of the space weather. The intensification is still difficult to do because the satellite that monitor the solar wind are very close to the Earth, so it's already too late to kind of late to do the alert, and so we don't know how after the coronal mass ejection was released from the sun. We don't know. We don't have satellites almost in between in the interplanetary medium that measure the direction of the magnetic field. So that we don't also have good models because it's difficult. The magnetic field direction may change. We know the direction when the coronal mass ejection is released, maybe by solar probe or some satellite that's close. But during the propagation in the interplanetary medium, the direction of the field may change by interacting with other structures and turbulence and things like that. So when it arrives to the magnetosphere, it's already with the direction change, and we don't know what would be that direction. So that's important issue for people who are interested in forecasting space weather and magnetic storms. Very difficult to do especially do it to that problem.
Okay, thank you, doctor. That's what a very good response because I think only in the maximum and minimum solar cycle, but all these processes related to the evolution and the propagation of the CMEs are very important to create these processes of reconnection. So all this evolution of the CME is very important. Thank you, doctor.
Yes, that's correct. Yeah, right.
Thank you very much, Dr. Gonzalez, for the talk, and to everyone who attend. Very interesting thought about the magnetosphere, many topics. Um, we will share your email for further question. Okay. So right now I stop